Good day, everyone. So today, the topic that I am going to discuss is on the shape and topology optimization of PM machines, particularly IPM, uh, for the high-speed drives. So, before I start, I would like to acknowledge a few of my team members: Will Cross, Ron, Rob, Grant, and Bhupesh. So this is a team effort. So we have been working together to come up with some robust optimization process uh, on how to really get into the roadmap of optimization for this e-machine design and validation process. So if we really look at the scenario at the current industry, so many of our off-highway industry is trying to get to a high-speed, high-frequency drive uh, because of many considerations. So this investigation is also required a separate kind of characteristics of e-machines, which are not typical in the regular drive systems. So we are talking about high speed and high frequency. So the design aspects are different, and that needs to be considered. So one of the myth that we usually have is off-highway vehicles are very huge and they have a lot of space inside to fit any kind of a machine, which is not true. And also for the market or the systems which are currently available in the market, so there are very limited scope of getting the same characteristics, same performance, and same user experience. So we there are a limited scope of operations that can be altered. So majority of the time, so we need to have the system performance either very similar because those are the customer requirement that we have to keep in mind. So, but as we are already seeing, the industry is moving strategy towards the high-speed operations drive. So it is very critical for us to understand what are the considerations and how actually it is going to affect the overall system and overall design of our complete ecosystem. So this study was basically designed to understand what topologies that we could get into and what are the boundaries that we could hit that could be considered if we really want to step into a territory where we want to operate our machines or our traction drive at high speeds. And the high speeds that we are talking about are basically more than 15K RPM. So if we really look at the overall design flow of e-machines, so, and that is one of the reasons why we wanted to have an integrated approach because we wanted to spread across length and breadth of different ways that we actually analyze our systems. So this is basically a gist of what actually we would like to have. So one is on the conceptual design side. So this is basically to understand what machine combination best fits the requirement as of now. So that could be analyzing off-the-shelf component or doing some regular changes or doing a new design with the suppliers in place. So some of the things that we would like to understand are basically what are the top speed curve, where actually the slot or pole combinations, the inertias, the specification, and the materials. And moving to the right, so we also so once we have some design, so we would like to understand a little bit more that forms a basic design, which is more to understand the overall electromagnetic performance. But once that is satisfied, so we also want to talk to the system engineers to understand what they think about. So, do we have an inverter available for it, or do you want to develop a new inverter? What is the system efficiency? What is the fault variability that you can handle? And what are the other challenges that you already faced in the system, like shaft voltage? So, do you want to understand all these things with the new system that we may be proposing? So once that is done, so obviously the uh, all these details will feed into our system environment where we are trying to more understand on the control part of it. So how do you control our e-machines? So is it controllable? So what actually is the saturation points for this design? So is it comparable to the machine that we had earlier, or it is going to drastically change the whole control algorithm? Can we reuse some of the components that we already have? So all those decisions are taken there. And finally, the system level optimization where functional testing, we also have field systems. So, and also if we go down on the vertical side, we also would like to have a check on the thermal performance, the overall temperature distribution, and also like to have a cooling system optimization because we would like to stick to the all our machines basically are uh, aggressively cooled, oil cooled machines. So we have a limitations on what is available for the system. From the system, what is available, coolant that is available. So we also want to have a check on that. So when we talk about optimization, so we want to spread across both depth and breadth across this design frame. So that is very critical to have a integrated framework for us because we want to talk to a single model or a single domain across all three different systems. So we don't. So as much as possible, we wanted to utilize common component that includes a common material base, a common winding specification. So just to understand, okay, we are talking in the same terms. So we wanted to have a single tool chain that could possibly do all this for us. So that is the roadmap that we have for the overall optimization as a workflow for the machine. So if we talk about the current project as of now, so the scope of this project was more to understand for high speeds what are the different architecture that could be taken into considerations, the costing, the winding optimization. So also we wanted to have a targeted cooling approach. So we wanted to understand we already have a target that we cannot extend system performance or the system coolant requirement over certain limitations. So we wanted to make sure that we maintain that requirement so that we don't have to change any major changes in the overall system ecosystem. So and as high speed drives, we also wanted clear understanding on where are we hitting our structural limitations on the design strength and also on the torsional vibrations. And the complete then hook up everything into the drive system for system optimization. So if you look at something on the overall the approach, so if we take a baseline on the current scenarios, so these are some technical targets that we wanted to achieve in this course of time. So in a course of maybe 5 to 10 years. So basically the cost per dollar for kilowatt hour. So basically as of now it is somewhere between 50 to 60. So I think we wanted to hit somewhere between 50 to 20 at some point of time. The power density, we wanted to achieve a higher power dense machine. We wanted to achieve a continuous power density to a different level in terms of kilowatt per amp, and also the overall drive efficiency to be more than 92%. So this is something that we have in mind, and we are still working towards achieving some of those targets. So if I talk about the overall motivation, so as this is the very first step, so we decided to take the one of the critical component of e-machines, and this slides explains more towards why we took rotor as one of the first component to get optimized. So if you look at the bar chart, so that is basically the critical or reference IPM overall cost distribution of material. So 53% of the cost is from the magnets, and other things are basically the housing, copper, shaft, and laminations. So 53% of the cost is coming from the magnets, and that sits in the rotor. And if you look at the approximate weight distribution, so magnet is basically close to 5%, and the the major component of the weight is 41%, the stator core, and that is only taking into account maybe 19% of the overall material cost and weight distribution. So if you compare these two graphs, so our thought process was if we optimize the rotor and the magnet, the overall cost, so we can hit a cost number which is more decent and more optimum for our overall project. So we wanted to understand, can we do something on the rotor side, and then we hit the other parts, because that will become little critical for us. So this is more about to understand the overall application requirement and concern that we had. So we already had a baseline machine. We did a lot of testing and a lot of simulation benchmarking. So some of the performance parameters that we analyzed were basically the electromagnetic performance, the torque per amp, ripple, also the torque segregation. We wanted to understand, do we have enough variability of getting into the flux weakening zone to get the more relentless torque at some point of time, and also what actually is that, how much it can understand. So we wanted to understand the overall torque segregation, of course the loss map for overall thermal characterization, and rotor structure stability. So these were some benchmarks that we had. For example, if we consider the max speed of the baseline was x, so we wanted to hit a target of 2x or maybe higher, and we did some understanding and study, and came to uh, a conclusion that, okay, so if we want to use the same baseline machine or use the same baseline design, maybe 50% of it, so what are the possible options that we could achieve that target? So one was basically scaling it radially, so that it can achieve that maximum speed, and also getting onto a new pole number. So we wanted, so these are the two brackets that we wanted to understand. So if the base machine design remains 50% common on the stator side, and you only want to change the rotor, so what are the possible options that we can come up with to get to the max speed that is required? So there are two different machine options that we are working. So one is scaling the machine readily, another is scaling the machine readily, also changing it to a new pole number. So some of the things that the we consider variabilities, of course, the slot pole combination, the dimensions, the distribution of winding, and the overall active length of the machine, and the inertia, because this whatever machine that we are proposing has to get integrated into the drivetrain. So inertia keeps a major role. So we wanted to keep the inertia either the same or maybe a little bit lower, so that they don't have to change the overall drivetrain switching or drivetrain design to a major extent. So that was the constraint that we had. So if we really look at the constraints, so we wanted to have a higher torque per amp, or maybe a same TPA number for as for the baseline. The overall rotor volume similar to baseline. Losses, we had a chance of 10 to 15% extending the losses, because that will hit our thermal limits at some point of time, and the system cooling performance. Inertia comparable to baseline. So these were some of the trade-offs that we wanted to understand with this current project as of now. So before we went to get into optimization, so we wanted to understand how actually what is our baseline. So where do we stand as of now? So for a complete baseline correlation, we also wanted to understand what are the manufacturing variability that we can achieve or we can understand from the EM simulations. So some of the things that we have considered as a manufacturing variability are lamination factor, that is going to influence the stator rotor, the lamination saturation, the residual magnet strength of the magnets, that is after it is being completely assembled and completely uh, assembled into the rotor system, and also the magnet temperatures where actually our magnets are operational. So we had a DOE study of these manufacturing variabilities, and we have come up with a number which best suits our design for the baseline. So on the right, on the top, we have that comparison of torque, which I put to test. So the blue indicates the rated operation, and the orange or green indicates the peak operations. So if you look at the base speed, so basically we are within the 5% for both base speed for the both rated and peak operations. For higher speeds, we are close to 3%. So I think we are good with the whatever the manufacturing variability that we're considering and with the test data. So our baseline model is pretty correlated and we can do optimization on the baseline as of now. So, and also the left graph shows the overall torque component segregation. So basically, we wanted to understand how is the relentless torque and how actually this changes with the phase advance. So as you can see that after some, so it this design that we currently have, so it doesn't have a much variability with respect to the electric torque. So the magnet torque, electric torque almost same after some flux weakening. So we do have some scope to improve on that part also. So, but so this gave us some idea on what are the areas that we could take up for getting the topology optimization or getting the inertia reduction. Uh, so if you look at the right graph, so that's the flux distribution, and also we have identified some areas where we would like to have a little bit more reduced material, so that are not actively participating in the torque production, or it's not actually getting saturated. So we wanted to have a little bit more, so we could push a little bit more saturation in some of the areas, and the ones which are highlighted in the rightmost figure. So that is something that some of the areas that we are targeting to optimize in the rotor, of course, including the magnet dimensions. So this is the framework that we are actually working on. So the left framework says of integrated framework. So first was to create a parametric baseline model. So because we wanted to develop a model within the same software ecosystem, because that is going to the parameterization is going across different domains. So we wanted to have a single model. So we wanted to develop a model which is parametric inside the same software. So we were able to do it. Our own customization. So we were able to create a parametric model. I think there was a good session yesterday on how we can do it using the scripts, and we have utilized some of those options to create our own parametric model. So the next thing was we change in the design. So we also see a change in the overall the optimum gamma angle for the system to be operational at a highest efficiency point or the highest torque or power point. So we wanted to understand that for each design. So we utilized some of the example files that we already have to automate that whole process and implement that into our system. So we also have a batch, the script that runs a motor inductance calculation and back calculates the best gamma angle for the system that is then taken forward for the electromagnetic performance. So here we are taking care of torque ripple, voltage limits, and the losses. And then on the edge optimum design, we also want to understand the structural performance, where we are taking into account the stress, displacement, and inertia, which is calculated. It is not a direct output as of now with the tool. So we are actually calculating based out on the rotor area that is being provided as a one of the equation-based input that we are developed. So inertia is being calculated and it is being kept at a check to make sure that we don't hit a number which is higher, because we cannot go lower on the numbers or we cannot go higher on the numbers because the system performance changes, and we don't want to do a lot of changes in the drivetrain as of now. So the first initial thought that we had was to have a one-way coupled analysis, but that was taking a lot of time. And then we chose to opt for a sequential analysis where we have all this one completed one by one. We don't have to couple any simulations because the parameters are because this is a complete ecosystem in a single tool chain. The parameters, the CAD parameters and the performance parameters can easily transfer or can easily be referred across different domains. So sequential analysis was also helpful. So this is something the route that we are taking as of now. And if you look at the overall variables that we are considering, so ID, OD of rotor, We also have introduced a few inertia reduction geometries in the specific areas. We want to optimize those geometries to understand the best possible inertia that we could get for that each machine design. So we also want to include the air gap as one of the constraints because air gap is something, it's a manufacturing variability. So any air gap is not suitable. So we have a limit or constraint on the air gap. We also want to have a limit on the active length because we don't want to have a very long rotor because that will have a different kind of scenarios inside the drivetrain. And then the major part was the magnet position, the magnet angle, and the magnet dimensions. Here, we also are taking into account the number of turns and the resistance. But as of now, it's a linear behavior. So we are not actually considering the actual resistance with the change in number of coils. But we have a linear behavior system that has been implemented. So with each change in turn, the resistance changes accordingly. So once we have the optimal design, then we do a complete analysis of that. And as per the response is considered, we are keeping a check on the torque and other EM parameters. So here we also, as we are changing number of turns, we are also taking into consideration of the slot current density. So we are keeping a check, or we have a limit of the slot current density because we don't need a really high slot current density because that will increase the losses. So we have a limit of 10% increase from the current design, so that we can have a limited thermal performance or a change in thermal behavior. We also are looking into rotor surface area, and using this number, we are trying to calculate the rotor inertia. We also taking care of rotor displacement because that is a direct output that we have from the system. So if by any chance the rotor inertia is uncalculated, so we keep a track on rotor displacement and the overall stress in the system. So these are the variables and the response data that we are tracking. And if you look at the setup, this is something that is very generic. So we are using multi-objective generic algorithm. We tried the basic generic algorithm, but that is useful to generate the basic design space. So what happens is, if you directly go to a multi-object generic algorithm, you end up with lot of cases that are not actually productive. So what we did was we just ran a simple generic algorithm to understand what are the designs and what are the dimensions that the machine can take, so that we can limit our dimension variability to a certain number, so that we don't hit the number of unresolved cases to a high number. So first we did a generic algorithm sweep that gave us some baseline about what are the dimensions that machine can take and what are the dimensions that is out of reach. So based on that, we decided our own dimension variability. For example, what is the max rotor ready and what is the minimum rotor ready? What is the max dimension for the magnets that this machine can take up? And so this number of generations are basically dependent on number of variables. So this cannot be less than the number of variables that you have. So it has to be a number which is higher than the number of variables that you have. So for us, it is somewhere between 10 to 15. The population size is basically 20 to 30. This can depend upon your own user experience. So once you see that how the from each generation, how actually the case is changing to a more valuable data point for you, you can change the population size to reduce the overall time and the and the data in the system. So it 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 does have a lot of results. And always keep a check on geometry errors. So basically, I don't want to run a case with geometry which is not feasible in design. Basically, rotor getting into the stator, or so all those geometry checks, I keep it on so that I don't end up with running everything that is not feasible. So just for our constraints, so I just have given just think through. Basically, what I am talking about is there are few scenarios that you need to take into account. So phase angle range, because you don't really have to run a complete sweep of 0 to 90 or other operating points, because it will just it will increase the number of cases for you. So once you have some baseline, so you know that the maximum efficiency point is between maybe 20 to 60. You don't have to go beyond that. So that is something that you can keep a check on. That will give you a little bit more design space which are most usable, and it will and you can cut down on the number of population size. So if you are taking structural modeling into account, one of the critical point is how do you actually model the magnet contact modeling, because you are changing your magnet CAD parameters. So the magnet contact points are very really important, because you are also so this the magnet contact points are basically giving you giving you the little bit more information on the overall stress limits that the magnet is hitting. So you need to be very careful how do you model the magnet contact. So as this is a more sequential kind of a approach, so design variables would talk to each other in different ways. So you have to have a check on how do you name your design variables and grouping them, so that we don't end up creating when you look at the operating function or the CAD parameterization, you don't end up giving different numbers for the same design parameters. So design variables naming and grouping is little critical. You also need to have a check on your structural properties. And also, as of now, we are not faced any issue with changing the analysis sequence. So basically, what actually I'm talking about is what it is a sequential calculation. So we don't know what has to be run first, run second, or run third. So usually that grouping will be critical at some point of time. So this is something that I will talk you through some results now. So this is the map that you usually get out of a optimization from this tool. So basically, you quickly can check where actually the optimization going through. So this will give you a quick indication on okay whether so if you take a look at the average torque, of course I am getting a higher number of the red means it is on the positive direction as per the optimum function, and uh, and basically the blue means it is in negative direction. It is helpful for some cases, and it is not helpful for some cases. So this is just a color code. So this gives you some indication about where actually the optimization has gone through. So was it able to generate everything that you wanted, or you still have a scope for some of the uh, or do you still whether the overall number of child cases or number of population sizes is good enough? Are you able to achieve the required optimum function, or you still have some scope for that? So this gives you some indication. But if you go a little further, so here I am focusing on the torque, and if you can see that I am basically stating how actually from every generation the multi-operative optimization has converged to a more optimum results. So if you look at the generation zero, so it has set across all the data points that it would have. So, but as it has gone through the Gen 5, Gen 10, Gen 12, so it has more segregated results towards the the function or the baseline. You see that you also have a very close connect with the baseline for most of the cases. So this gives you indication that the optimization is going in the right direction uh, for most of the cases. So if you look at the electromagnetic performance, so here I have the average torque on the available DC bus voltage. So the box indicates that these are the populated sizes that I can consider for the machine design. So these are the optimum cases as per the constraints that I have set. But if I want to remove some constraints and I'm happy with some of the constraints to be gone, so you also have a bunch of cases about about that body of work. So you can consider if you can push the system to a different level. So this gives you indication that okay, this is something that I can work with, and this is something that we can also have, but that requires some system changes to be made. So and all the cases may not be applicable for you, because depending on size and shape, so there may be few cases which will fit directly into your system, or there may be few changes are required. So this gives you some indication of where actually your system is getting operated. If you look at the next structural performance, so what I have is I have mapped rotor stress and the rotor area uh, based on the average torque. So if you can see that there are a lot of scope where I can easily get the highest torque and also reduce my rotor area, and back to I can also reduce rotor stress. So, and also a lot of other options above that bounded region where I have a lot of scope of getting a higher torque, but the stress are going to be very high. So I don't want to hit that region at all. So you have a lot of options which are available where you can reduce a lot of rotor area and also get a lot of torque. But what you can also see is indirectly you're also reducing some cost because you are reducing the rotor area by close to 15-20% some point of time. And this is the inertia as one of the critical factors. So what I am talking about is the overall inertia of the rotor and also the displacement of the rotor. And as you can see that you have some cases where you have the torque is above the baseline, and you also have reduced the inertia, and you also can pinpoint on what is the number that you want to pick, and do search on particular area to see, okay, these are the four destination options that I have that basically will not alter my drivetrain system much. So so this is some comparison that I'm doing as of now. So if you look at the three different designs, so the baseline is what we had, radial scale and the lower poles. As you can see that the design has shrunken a bit. So with the compared to the baseline, the radial scale and lower poles, the design has compressed a bit. Sorry, for I was not approved to show the complete design, so I have to mask some of the features there. But the main idea was to basically to give you a visual representation of uh, how the machine designer shrunk. So if you look at the overall raw material weight distribution for all the different components, so basically if you compare copper from for baseline, radial and roll poles, so it has come down to maybe uh, 4 to 5 kgs from 7 kgs. On the magnet side, we have reduced close to 50% of the magnet. It was 3 kgs. Now we are operating somewhere between 1 and 2 kgs. On the overall iron, so we have reduced 10 kgs. And the overall total weight, so we have reduced close to 15 kg of the machine weight. And that is if you look at the production and the number of vehicles that will fit in, so I think it's a huge cost saving for us. So this is the overall costing and pricing. So if you look at the overall system weight, so basically this bar graph shows the as we are reducing the radial scale, so of course we are not getting the same power, same sorry, we are not getting the same torque, but we want to keep the power the same. So we want to keep the same max power. So what we are doing is we are keeping the power constant, and we are trying to have a gear ratio increased to get the required torque level. So compared to baseline, we have reduced the output torque by 40%, keeping the baseline power the same. And if you see the graph below on the overall variability with respect to the baseline, so the dual losses has come down close to 6%. On the lower poles, it is more. On the stator side, I think we have reduced. This is overall the losses distribution that I'm talking about on the copper loss, on the stator loss, rotor, magnet, and mechanical losses. Overall, we could reduce 20% on the radial scale and maybe 6% on the lower poles. So we know that we are going to have the thermal stability also with this new improved design. So if you look at the overall cost, so the overall cost of the raw material come down by 20%. So basically with the radial scale machine, we are hitting 0.84 of the baseline cost and 0.82 from the material cost. But of course, as we are decreasing the overall surface area that is available for the cooling, so it needs a little bit more aggressive cooling. So the raw material cost may come down for the machine, but uh, we are sure that there will be some additions on the cooling requirement. So that has to be reassessed. So, but the losses numbers say that we are reduced the losses, but we also reduce the overall surface area. So there will be slight increase in the overall cooling requirement or the cooling reassessment redesign. But on the overall raw material side, we are able to reduce maybe 20% of the cost from that. So this is my final slide. So as I said in the very first slide, so we wanted to go across the domain. So we wanted to have a integrated design process. So basically, we wanted to have a more robust data transfer between the structural and magnetics. So we were able to achieve it. So for the current study, multi-objective algorithm was bit fit, but before that, we also used geometric algorithm that give us a design space that we can work with. That was the added advantage. So actually, the grouping and sequential calculation approach provides the opportunity to uh, enhance the design space across different domains because coupling or doing a one-way coupled analysis is a time-consuming approach. So this is something that we can stick to as of now. So other thing was we wanted to have a cost matrix inbuilt to keep a track, but that is not readily available as of now. But it is something that we wanted to have integrated into the framework approach. As of now, it is just a manual calculation, but we would like if it is something that we have it basically into the tool itself. So that is my final slide. So I am open for questions.
Uh, Thank you, Sashi sir. So we have a few questions here.
Sure.
The first question is, what is the accuracy in simulation you look at for a detailed analysis?
So as of now, for the baseline machines that we have already tested, so we are able to achieve close to 3 to 5% of the variation. But it also depends on the manufacturability and everything. But as of now, uh, we have reduced our correlation matrix from 10% to 5% because we are able to achieve that as of now. And I am talking on this 5% in terms of torque and voltages. Losses is not considered because ours are force pull machines and mechanical losses and the other losses in the system like churning losses cannot be calculated or tabulated. But on the EM side, I am considering the torque voltages and the flux linkages. With that, we are close to 3 to 5%.
Okay, so the next question is, are you using analytical models in your framework or only 2D FEM?
So for the baseline, we did a complete 3D model and 2D model comparison. Uh, but as we are not considering the leakage fluxes and other things as optimization for the current design, so we did not see a major difference in overall torque production. Of course, there were 1% or 2% increase and decrease in voltages and torque numbers. But for the complete optimization as a framework, we are trying to stick to 2D, but the framework will be extended to 3D once the once we get the complete optimum results. One or two model will be taken into 3D complete FEA and then transferred something into the thermal modeling. It is more to CFD. So as of now, for the cost matrix, we are sticking to Excel and some other tools, but apart from that, everything is in 2D.
Uh, Shall we move to the next question, sir?
Sure.
Yeah, so is rotor inertia an important constraint in eccentricity analysis?
So rotor inertia is critical for us because we are trying to get this integrated into the drivetrain, and the drivetrain already have some restrictions on how actually the behavior should be. we cannot completely redesign. So inertia is a critical factor because we need that initial torque and initial response, and also the user experience for the existing design was required. So we did not wanted to have major changes in the our overall drivetrain or the gearing principle. So inertia was something critical for us because we wanted to have the same user experience and the same drivetrain function. Inertia is also very critical at some point of time because we also wanted to the whole torque that is required for our machines are very huge, so we cannot operate at very low inertia, and after and even for the higher inertia, so we need to get to a higher current levels to get the machine running at very low rpms. So we wanted to have a balance across, so we already have a baseline inertia number. So that was the reason that we wanted to keep it little simpler and wanted to have something within the our body of framework for the inertia. But if you're okay with something for your, it all depends on the system performance that you want to achieve as a at a user as a user experience level, and also on the because if you have iron here, then you need to push in more current at the stall condition, and that is something that we did not wanted to have.
Uh, okay, so sir, the next question is, did you get enough accuracy with 2D calculations? Usually, corrections with 3D results are needed.
So one thing that we tried to do was replicate some of our test lab results with the 2D. And as I said earlier, so we identified few parameters as a manufacturing variability. So typically the magnet temperatures and the overall machine saturation are the few areas that are basically changing with each machine design, or that is easily not, they are usually estimated. So if you even look at the test, so they don't actually exactly measure the magnet temperature, or they don't exactly measure the saturation. They are estimated based on the manufacturing processes or other priorities. So we decided to play with those correlation matrix to get to our design. So for a particular machine design, we have fixed that okay, these are the numbers that we are going to use for all our simulations, and as of now it's working for us. So basically we vary those few parameters and make sure that if we have a test results, then of course we would like to match the results with them. So as of now, it's working good for us. But on the losses, of course, we need to have uh, correction factors because JMAC doesn't include the mechanical losses or doesn't include the churning losses. So that needs to be added externally to get the efficiency number. So efficiency numbers are not directly correlated with the what we have from the tool. So we need to have external correlation matrix to be included if you really want to get the correct efficiency number. So any questions? think this is what was the calculation time for optimization calculation. So for the current study, it took close to 9 hours, 9 to 11 hours, depending on the license structure and other things. And this was run on local system. Hello. Okay. Okay. Yeah. I think I have no further questions that I can see. So thank you for listening to me.
Thanks, Shashikiran. Sorry, I think Haridas left in between.
Yeah, I
So,
think he just messaged me that
correct,
there is some issue there.
correct.
Okay. Yeah.
So there are a couple of questions. What is the
Mhm.
accuracy in simulation you look at for a detailed analysis?
So as I said, we are looking. We had a bracket of 8% before, but now we have come down to 3 to 5% because we are able to achieve that.
Great. Okay. So are you using any analytical models in your framework or only 2D FEM?
So as of now, we had a baseline comparison for 3D and 2D, and we are satisfied with 2D for the optimization as constraint. Uh, as of now, there is no analytical tool, but we only have analytical tools for overall efficiency and loss calculations because some of the losses are not included in the tool, such as mechanical losses or the other losses that are part of the the churning losses or other losses which are not part of the electromagnetics. So for the overall system efficiency, so we have to use analytical tools to or a better correction model to get to a better efficiency numbers. Apart from that, this completes optimization was on 2D.
Thanks, Shashikiran. Then, so I think these are the questions I think already answered. So for backup, I just fine. So thanks for joining the session. So I think everyone had a good session. So by 2:30 we had another session. So keep wait there, and in the agenda you have to see and view session. And once you are once the time starts, you can log in the sessions. So thanks, Shashikiran. Thanks for joining.
Yeah, thank you everybody.